So, let's begin. We're going to take a look at graphs of linear equations now. In the last class, if you recall, we looked at relations, or we looked at simple equations with two variables, x and y. And we came up with the concept that how many solutions are there to any equation that's in both x and y? How many solutions are there? How many? Two?
X and y.
Okay, so there are two parts to a solution. Okay, that's all right. But how many solutions are there? To any equation with x and y, how many possible solutions can you come up with? Infinitely many. Again, you can plug in any x value, and what happens? You get a y value. Now, obviously, as Tristan said, there are two parts to the solution, and that's known as a coordinate, x comma y.
What about like line segments? Is that an inequality or?
A line segment versus a line?
Yeah.
A line segment would still have infinitely many, believe it or not, because technically between every point, there's another point. So between 3 and 3.1, there's 3.01, 3.02, 3.03, 3.0, you know what I mean? So theoretically, there are infinitely many solutions to any line or line segment. It's a great question. Okay, he's saying, what if the line doesn't go on forever, right? How could there be infinite solutions? Because between every point, there could be another point. There can always be another point between any 2 points. That's kind of weird to think about. Make the smallest, make the smallest deviation. 3.0002, 3.003. Well, those are two different points for x, and those would give you very small differences in the y values, giving you another point. So you can infinitely choose as many x values as possible. We're going to look today at the graphs of these equations, and we're going to look at two variables. Then we're going to look at ones that are in this form, which are horizontal and vertical lines. And then we're going to look at intersections of two. So let's go ahead and get started with this. The first and simplest method to ever use for any single function is just graphing by plotting points. Now, this is not very efficient as a method, but we're going to use this first to demonstrate what a graph looks like. So go ahead and pick 5 values for x, please. Whatever values you would like to choose independently. Pick 5 values for x, and then determine the 5 corresponding values for y. On your own, pick 5 values for x, and then determine the 5 values that correspond to that x with the y coordinate. Something that I recommend you do, and I was telling this to my class last year, is keep a graph paper in in your drive folder, so that when you're on your iPad, you don't have to always load graph. Oh, you guys have Notability actually, right? Isn't there graph paper in the background? Can you load small graphs though?
If we take an image and crop it.
Okay. So yeah, I save an image always in my Google Drive folder, so that whenever I need a graph really quick for my homework, I can quickly just hit the plus sign and add an image and pull it right from the Google Drive folder. So you always have a graph if you need it. And you could just go to Google and type in, obviously, like graph paper image, and you could save any image, whichever one looks best to you. Now, if you didn't do this, you don't have to, but I would do this personally first. I would solve for y, just because if I'm going to choose x and then determine y as a result, I don't want to have to solve for y 5 times. I'll solve for y once and then plug in the 5 values for x. Oh, and give me 5 numbers. Go. And make them some negative, some positive.
Negative 10, 2, 3, negative 6, 5.
All right. That works. Again, it doesn't matter what numbers you choose, right? It makes no difference. Now, the corresponding y values, we simply plug in the x value. Negative 10 plugged in here makes this negative, well, it makes this positive 20, and 7 gives us 27. Plugging a 2 in gives us 3. Go ahead, Ash, you got it? Plug a 3 in gives us, plug a negative 6 in gives us,
19.
and a 5?
93.
Good. Okay, those are our 5 coordinates. Now, yeah, go ahead.
Did you have to do out the whole equation? I just did it based on, like, do you have to simplify the equation?
No, you don't have to, but what I'm saying is that if I'm going to solve for y, I might as well do it once and then plug in x 5 times. Or else you got to plug in x 5 times and solve for y every single time, right? It's an extra step, or an extra 4 steps you're getting out of that. So yeah, these are my 5 coordinates now. Look at my graph. And I'm really glad you picked arbitrary, large, and random numbers, because most students pick 1, 2, 3, 4, 5. And graphs are always nice and simple, and it's really easy to do that, obviously. But I want you to be prepared to draw a graph for any set of values. So what's your biggest x value? What's your biggest x value? Biggest, George?
5.
And smallest?
-10.
-10. So that spans 15 units. Does everybody see that? From -10 to +5 is a span of 15 units. Well, look across here. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Ooh, so close. I could almost get all the points on that graph. So I'm going to go by 2s just to be safe. Or 1.5s. It really does not matter, okay? But I know I need to go as far back as -10. So at this end, I'm going to start. Let's go ahead and draw my graph skewed to the left a little bit. Oops. I need a straight line feature on here. There's got to be one.
If you just hold down, oh.
It's on, that's on,
Not notability.
I know, it's on notability. Here, I got one. This will work. All right, so I'm going to let's make my y-axis right there. Now on the y values, what's my largest y value? Anybody? Largest?
Oh,
What is the largest y value?
27.
27. Smallest? -3. So clearly, I'm more concerned with the positive part of the y coordinates. So I'm going to make my x-axis down here somewhere. Again, yours is different based on your numbers, right? But you need to think about this kind of stuff. This is how you approach graphing here. So that's what my graph is going to look like. Do you understand why I specifically made it look that way? Again, very few negative y values. -3 is as far as it goes. But it goes all the way up to 27. So I'm going to go by 3s on the y-axis on mine. Again, I'm going by 3s. So this is 3 here. This is 6. This is -3. Do I need to label every single value? Do I need to label every single one? What do I need to do? I need to establish what? I can stop at this point because I've already established what I'm looking for. What have I established by putting at least a couple of values here? What have I established? Where 0 is, okay, that works too, but that's always the origin, but that is true. What else have I established now? Sure, the units of each one, so how much they're going by. So what's that term that we use for that? What would that mean? You're establishing maybe a trend, or you're establishing a change, a consistent change. What is my consistent change along the y-axis? 3. What is it?
I thought you were saying the term for it. So
What would you say? What were you saying?
the rate of change.
Rate of change, that works. I'm going by 3s, the rate at which I'm changing. What should I change along my x-axis in this case? What did we say? We need to get back to -10 and up to positive. I should actually slide my y-axis over a little bit then. Right? If I'm going all the way to -10, let's see if that works on this now. Can I do that? And can I slide these other ones over at the same time? Unfortunately, I can't slide it over. That's annoying as hell. All right. Oh, there we go. Why did I slide it over a little bit? Because I'm realizing, we need -10 for x, and the largest x is only going to be 5. So in this case, I might go by 2s now along this way, or 1.5s. It doesn't matter which one, as long as you can cover all of the data values. If your domain is covered and your range is covered. So realistically, if I go by 2s, I'm going to get all the way to 10 right here. And by 2s, I'll get to -10 by here. So I can go by 1.5 to get more use of my graph here. So if I go by 1.5, I can put 3 after 2 boxes and -3 after 2 boxes. And that establishes a trend also. Again, if I know that 2 boxes is representative of 3 values, or 3 units, then 1.5 is each box. 1.53, 4.56, 7.5, okay? So I'm going by 1.5s. It does not really matter, yeah.
The teacher that taught me this said you should always have the same unit since it's the same square.
In one direction you should, absolutely. But never is that true vertically versus horizontally. You're going to see this if you study engineering. There are things called log graphs. And logs, actually, they go up by factors of 10, while this one goes up by 1. So graphs will not ever, in real life, you're going to see graphs, the x-axis and the y-axis will not be the same value changing. But it needs to be consistent on that axis. So I can't do this, ready? I can't go 3, 6, 7. That wouldn't make sense clearly to you, you know that. But along this direction, you absolutely can actually. And that's okay. And you're going to find that at times you need to do that. Because what if you're plotting here years, and this is population? Come on, think about that, right? Years go up by 1, 2, 3, while population goes up by millions. So clearly the boxes can't be the same value. But along one axis, those changes are consistent. But each axis is different. All right, now I go ahead and plot these. So negative 10, 27. I'm just going to point so we're clear. I go to negative 10. This is negative 3. This is negative 6. This is negative 9. This is negative 10.5. So negative 10 is around here. And I have to go all the way up to 27. 3, 6, 9, 12, 15, 18, 21, 24, 27. There's my coordinate right there. And I just lost it. Is it right here? Is that where I was pointing? Is that correct? I looked at the side for a second. 3, 6, 9, 12, 15, 18, 21, 24. Whoop, up one more. And now, of course, I can't erase this. Let's see if I can move this one up. This is so annoying. So it's great that I can record on this app, but it's not clearly as good as Notability. Okay, this is not there. Make believe, please. I just can't erase it for some reason. Once it's there, it doesn't allow you to erase it. I don't know why. All right, so that's the first coordinate, 2, 3. So 2 is right here, 3 is right here. That's an easier one. There's the second coordinate, 3, 1. So for this one, we've got to go to here, and a 1 will be, in this case, since we're going, I apologize. 2 is right here. There we go.
How do we know that the line is negative again?
A line is negative. What do you mean?
Its slope is down instead of positive.
How do we know? You could look at, well, we haven't gone over this yet, but you could look at the slope right here, and that's the negative 2 is the slope. Because this is in mx plus b form. Yeah, we're going to get into that in the next 2 sections. For now, I want you to get the idea of general graphing, and then we'll get into functions themselves. So, not yet. I mean, you probably do have prior knowledge of that, so that's okay. 3, 1 is going to be right here. Negative 6, 19. Negative 6 is back here, right over there, and up 19. 3, 6, 9, 12, 15, 18. 3, 6, 9, 12, 15, 18. Okay, what are we noticing right away as we continue to put points on? Do we need all these points? Do we need all these points? Yes or no? George, how many points do we need? 2. All we need are 2 points to make a line. So when you're making a line, it doesn't matter what 2 points you use. It really doesn't make a difference. In a moment, we're going to see something called graphing by intercepts. Well, there's 2 intercepts on a graph for a line. So those are the 2 points we'll use. But what I'm trying to point out here is that you definitely do not need all of these points. So let's go ahead and grab a straight edge, please. Use a straight edge of sorts. And go ahead and graph your line. Okay, it should be close to this. Okay, I'm approximating it with that line. But that's what our line would look like approximately. Okay? Again, when you're doing this on your own, you need to use a straight edge. If you're using iPads, a lot of freshmen had trouble with this last year because they were putting an object up to it and it was causing it to create a line. Use your ID card. It's plastic. It won't respond to your finger. So put your ID card on there, hold it with your finger, and draw a straight line if you need to. Oh, but yeah, you have that's true also. You have the automatic feature. All right, so we get the idea here. Clearly, as Tristan mentioned, it's a negative line because of negative slope. We'll get into slope in a little while. But for now, I want you to recognize that graphing by plotting points always works. You can always choose simply 2 points and connect them, and you have a line. But give some distance between those points. It might not be useful to pick the points as 1 and 2 for x, and then you only have 2 points right next to each other, because connecting that line might not be as accurate. Pick 2 points that are far apart. When you connect them, you get a more accurate demonstration of that line. Okay, think about that logically, how that works, right? If you pick 2 points that are so close to each other, it's difficult to connect them with a line and expand that line, forever. What do we put at the end of lines always? Arrows. Why?
To show what they're going for.
Correct. Okay, and what do I put on my axes? What do I put on my axes always? Labels, good. And in this case, X and Y. Am I forgetting anything else? Do I need anything else? George?
Just a quick question.
Yeah.
In slope intercept form, I think you're making a mistake because it's not going over 6, but it's 7 to 5.
Yeah, clearly, again, that was only an estimate. So if I want to move this, George, you're right. I can move this up. Yeah, the intercept should be 7, which is just a little bit above that, really. And, of course, I can't move this line now suddenly. But, yeah, absolutely. Okay, again, it was just an estimate of a line. You need to mentally think about this right here again. This should be going through the point 7. So this is quite close to that. And this is 9 right here, isn't it? So I guess we could say that might be 7 right there. Okay? Yeah. Again, slope-intercept, you know already. So if a lot of you want to jump to that and see that, that's fine. Okay, but please recognize the following. You need labels on your axes. I'm really spending time on this now because I don't want to see a mistake on this ever. Okay, this is stuff that if you lose points for this stuff on a test, it's sad. Okay, you need labels. It's not always going to be X and Y. It might be distance versus time. You need the actual line with arrows on the end so we know that it's a line that goes on forever. And you need your different changes along your axis, so your increments. If it's a problem that there's a physical nature to it, you should also put units. So if this was like population versus time, the units of time would be in years. And maybe the population is by thousands of people. Or if it's profit versus time, this is in dollars, this is in days or months, whatever it may be. Okay, so if you have units, put the units on the graph. Where do units go usually? They go after the label in parentheses. So your units would go here. Okay, oh, it's not appearing. Give it a second. Your units would go right there. Okay? After the actual label for the axis, you put the units in parentheses there. Why is this not delaying? So using intercepts here, all you need are 2 points. So if we could find both intercepts, we could easily graph the function. How do you find intercepts? And obviously you could read what's on here, but tell me in your own words, how do you ever find an intercept? British.
Like in the equation, if like y equals mx plus b, the b is usually the y-intercept.
Okay, absolutely, that is true. But give me a generic answer, British. Not, what if it's not a y equals mx plus b?
It's just
Then how
like,
do you find it?
like on the line, just like where it intersects, I guess.
It's where it intersects the axis, I agree, but mathematically, how do you find intercepts is the question. How do you find them? Algebraically, if I gave you a function, you should be able to identify the intercepts within a second.
You put one variable as 0.
Yeah, you set the other variable equal to 0. You set the other variable equal to 0. So if you want the x-intercept, you set y to 0. If you want the y-intercept, you set x to 0. If this was not in the back of your mind already, you need to highlight this or write a big note. Because this will continue to come up in every single math class you ever take. I'm not joking about this at all. Intercepts are extremely important for applications of functions. When is the profit 0? Well, what are you doing? You're finding the x-intercept when the profit is equal to 0. That's what you're actually doing. You're finding the x-intercept in a function like that. Or when is there a trade-off between profit or between revenue and cost? Okay, you're looking for these points. Intercepts are extremely important, so you need to know this. Okay, so if you need to highlight this, and then this.
I just wrote set variable 0.
Set opposing variable, put maybe. Because you don't set, because if you want the x-intercept, you have to set y to 0. You don't set that variable equal to 0 because that's not finding its intercept. Okay, so to find the x-intercept, set the opposing variable to 0. So let's do that for this one, please. Some of you probably already jumped ahead, that's fine. Okay, go ahead and find the intercept right away. So find the x-intercept by setting y to 0. Find the y-intercept by setting x to 0. I'm doing this up here because this is really simple. You should be able to do this at this point. So I showed you the y-intercept. If you had trouble with the y-intercept, there it is. Find the x-intercept yourself at least. Okay, this should be really quick, right? It should not take you long at all. It should not take you long at all. You really don't even need the math. I'm showing the work here, but you could probably do this in your head. You really don't even need to do this that much here. I mean, I want to see that you know what you're doing at least, but this is simple math, right? Just plug a 0 in for those two spots. Now, why am I not leaving my answer like that? Why am I not leaving it as just x equals negative 4.5? Why isn't that my answer? Why don't I just leave it like that?
Because that isn't the intercept, that's like where x intercepts, we have to plot the point, which is the coordinate.
Yeah, you need a coordinate. All points are coordinates. So this point is negative 4.5. Well, what's the y value? How do you remember what the y value is? What did you do in the first place? You set it equal to 0, right? You set y equal to 0 at the top to get this. So the y coordinate must be 0 when you're looking for the x-intercept, and vice versa. Okay? Again, you're always listing these as coordinates. Now you just plot these two coordinates on a graph. I can scroll all the way up. I've got two coordinates now. I'm going to insert this image real quick. All right, let's quickly make some lines here. Okay, there's my x and y axis. I go up 3 units. There's my y-intercept right there. And I go back 1, 2, 3, 4, 4.5 units there. There's my x-intercept. I should dictate or write down that this is by 1, and this also goes by 1. Let me zoom in because it's tough to see that, sorry. Okay, so they're going by 1 on both axes. I know that this is my x-axis, this is my y-axis. I should have arrows at the end.
If you know those intercepts, you can just graph one.
Exactly. And just connect them now. As soon as you have 2 points, you know what a line looks like. Simply connect them at this point. All right, there's our line. Why does this have a rising trend to it? It means the slope, we'll talk about in the next section, must be positive. Okay, positive slope. All right, let's fly through the next few. Oh, let's look at these actually first. Graph the following in a coordinate plane. And this says y equals 5 and x equals negative 7 halves. Now, where's the y value in the x part of these equations? They must be 0, really, is what's happening. So what I want you to do is think about part A as this. Think about part A as 0x plus y equals 5. That's really what it's saying. And part B here is really saying x plus 0y equals negative 7 halves. Now, if I look at these equations like that, I can easily decipher, the type of line I have here for each of these. Try values for x and y. Pick numbers. Pick a number so look at the first one only first, please. Look at this one here. Let's see. Give me a number, it does not matter what number. Nick, give me a value for x. 1. If I plug a 1 in, what is y equal to? In this equation here, if I plug a 1 in, what's y equal to? 5. Give me another value, Luke. 8. If I plug an 8 in for x, what's y equal to? 5. So no matter what value I put in for x, what is y equal to? Which is where the name of this comes from, y equals 5. So think about all your coordinates that have y equal 5. Well, on a graph, I'm just going to draw a quick sketch this time. So this is part A. All the coordinates that have y equal to 5 all lie at this height. Up here. There's 0, 5. There's 1, 5. There's 2, 5. There's 3, 5. There's 4, 5. Negative 1, comma 5. Negative 3, comma 5. Negative 6, comma 5. I don't care what they are. All I know is that no matter what I choose for x, the y coordinate is always 5. Hence, y equals 5 is the equation. So what kind of a line do I have here? A horizontal line. Okay, this will always be a horizontal line. Jot yourself a little note about that. Whenever it's y equals some number, it's always going to be a horizontal line. And we call that a constant function. A constant function. Bridge.
So we're thinking about this, right? Like it would be a straight across.
Yeah, it'd be a line straight across. Yep, exactly. Yep. Okay, that's all it is right there. Again, labeling your axes, x and y, please. Labeling your increments so we know. Okay, something like that. How about the other one? Based on your first example, use your context clues and use your intuition. What will the other line look like? Kate? It's going to be a vertical line. And if you try any value for y, it doesn't matter what you plug in. X is always going to be negative 3.5. Plug in a 2, plug in a 3, plug in a 4, plug in a 5. X will always be negative 3.5. So what will that look like? On a separate graph, I'll draw this one so we can see the difference. Negative 3.5 is right here. And I know that it's going to be a vertical line extending from there. So these are my coordinates right here. Again, I don't need all those coordinates. I'm just drawing them to show you. So here's my y-axis. Here's my x-axis. And there's my line. Any questions about this with horizontal and vertical? I don't really think you should try plugging in points every time. You should, by the end of this, after practicing homework and stuff, you should really just memorize that when it's y equals, it's a horizontal. When it's x equals, it's a vertical line. Okay? Y equals horizontal, x equals vertical. How about this one? Find the value of k so that the point P lies on the line out. And this changes up what we've been doing. We've been really graphing everything so far, and now we're looking at an algebraic approach or something. Well, what have you guys been telling me the whole time? These points that lie on the lines, what do we know about them? Where do they come from? Where do we get these coordinates? In the first example, where we had to plot all those points, where did we get the actual coordinates? How did we get them? In the first example, how did we get the coordinates? What did we actually do? Rich?
We had to guess, or we had to just give values for x.
Yeah, we picked values for x and they worked for y, right? So those values that we chose, did they satisfy the equation? When you plugged in for x, you got an answer for y, which made the equation true. So take a look at this example. If the point P lies on the line L, it must make this equation true. It must satisfy the equation. So what the 2 and the 5, where do they go? What do they go in for? X and y. So x, in this case, was 2. That goes in right here for x. And y was 5. That goes in right there. So if a point, write yourself a note if you need to. If a point lies on a line, it satisfies that equation. As a result, you solve for k. All right, again. If a point lies on a line, it satisfies that equation. Does this make sense? Is it pretty easy? I hope it's a little bit of a review from what you've seen in your middle school classes. If it's new, that's all right, though. It's not the end of the world. We'll definitely take the time to go through this so we're all on the same page. Okay, there's only one more example after this. Okay, then I'll give you a head start if you want to spend the last couple minutes on your homework. Graph the two lines in the same set of axes and find the coordinates of the intersection. Then show that this is a solution of both equations. So you know what I want to do? I want to get those calculators out. Let's get those calculators out, please. Okay? And what I'd like you to do, please, is graph both of these. But to graph them, what do you have to do first? To graph these in a calculator, what do you have to do to the equations first? What do you have to do to the equations? George, what do you got?
Put in y equals
Close. You're halfway there, George. George was partially right, not fully. Does it need to be mx plus b, George? That's the same thing. Same thing.
It just has to be equal to y.
Yes. You just have to solve for y. It doesn't have to be mx plus b form, okay? It does not have to be mx plus b form. So the first one, how would I solve this first one for y? What do I do? What does y equal for the first one? I'll come around individually to work with you guys. Don't worry. You're helping? Yeah, thank you. Y equals what? Yeah. Okay, and I'm just gonna. I want you to see that it does not need to be in mx plus b form. So many people have themselves on that, and they got to get it in that form. No, you don't. Just move something over. Get y by itself. Move the 2x over. How about the second one? Simple, George?
Y equals negative 1 minus 3x.
Yeah. Okay? If there was a coefficient next to y, even there, we could divide by that coefficient on both sides. Okay? We don't need to be in mx plus b form. That's useful, but it doesn't have to be.
Isn't it useful though? It's just like y equals 3 plus 1.
Again, it doesn't have to be. It might be useful if you're looking at an application where it's useful to know what the slope actually means. The slope is the change in the amount of gallons of gas per unit time. Then it might be useful. But for this context, we don't know what this problem is about. So it makes no difference whether or not it's like this or like this for us. Okay? It doesn't really make a difference at all. So go ahead and put these in y1 and y2. Put these in y1 and y2. 4 plus 2x and negative 1 minus 3x. Go to your graph, please, to do this. I'm going to show